Hey guys, let's talk about conditional statements. And we did mention those in the previous section. Conditional statements are statements of the form if P, then Q. So we have a condition. If something happens, then something else will happen. P, the if part, we call the hypothesis or the antecedent of the conditional, and Q is the conclusion or the consequence. And the statement here at the bottom is really important to understand. It says that a conditional statement that is true by virtue of the fact that its hypothesis is false is often called vacuously true or true by default. So, for example, if I said, if you make a 100, then I will give you $100. Well, if you don't make a 100 and I don't give you a $100, then that is a true statement. So if the hypothesis is false, then it does not matter if the conclusion is true or false. So that's really important. You might want to make a note of that. So if the hypothesis is false, then the truth value of the conclusion does not matter. The statement is true by default. So consider this statement. If 0 equals 1, then 1 equals 2. Now, as crazy as it sounds, that is a true statement. Since 0 equals 1 is false, then it doesn't matter whether 1 equals 2 is true or not. We would say this statement is true by default or vacuously. All right, we're back to those truth tables. It says use truth tables to show that the logical equivalence of the statement forms. We're going to annotate with a sentence of explanation. So let me get a little highlighter going here. So we're trying to show the logical equivalence of this and this. Now, I want you to notice that we have three statements. Excuse me. P, Q, and R. So we're going to need to begin our table with all of the possible truth values and the combinations for P, Q, and R. So you might remember from last section that this is going to require an 8-row truth table. So if you want to pause the video and try to set that up and see how far you can get, I would encourage you to do that. And then pick back up and let's see how you did. All right, here we go. So we start with, sorry about the dog. Can we get the dog put away, please? Sorry about that. So we begin with all the possible combinations of truth values of P, Q, and R. So notice we begin with all of them being true. And then we can systematically work our way through all the possibilities until they are all false. All right, we see that part of this expression has P and Q. So we can easily fill in this column anywhere, that's an or, P or Q. Anywhere either P or Q or both are true. So notice in this column, the only place you have a false is the last two where both P and Q are false. Okay. All right, let's talk about this next column. This little arrow is our symbol for if P, then R. Okay. So this right here. So P arrow R means if P, then R. So let's look at that the only place that this statement is true is if P is true. The only place this is false is if P is true and R is false. So let's take a look in our table where P is true and R is false. So notice in the second row, P is true and R is false. So we have a false there. Okay. Let's see. Here's another one in this row right here where P is true and R is false. Okay, and if you keep looking, that is the only place where P is true and R is false. Notice the entire bottom half of this table, the P is false. And remember, if P is false, it does not matter the truth value of R. Notice these are all true. All right, this next column, if Q, then R. Again, you will look at the Q column and the R column. The only place that's going to be false is where Q is true and R is false. So we've got here, Q is true and R is false in the second row. And we have here where Q is true and P is false. That's in the sixth row. All right, moving on. Notice that we're just breaking into small pieces so that we can put it together column by column. I'm going to change my highlight color here just a little bit. So in this next column, it says P or Q implies, is the way we would read that, R. So in other words, if P or Q, then R. So whenever we have a conditional statement with this arrow, we're going to be looking for anything that's false would be where the left side of the arrow is true and the right side of the arrow is false. Excuse me. So we're going to be looking at this column and this column. Sorry about that. Okay, so we're looking for where this column is this right column that I have highlighted in green is true, and the one to the left of it is false. So let's see. That's going to happen here. So we have a false. That happens here. So we have a false. That happens here. So we have a false. Everywhere else is true. So the only time a conditional statement is false is if the hypothesis is true and the conclusion is false. All right, now we're ready for our final column. P implies R and Q implies R. And so let's see, P implies R and Q implies R. We're looking at, let me change my highlight color again. We're looking at this column and this column. And because we see this little and symbol, the only place those are true is when they're both columns are true. So this first one, we have true, true. Here, true, true. True, true. True, true. And true, true. So we're supposed to show that this statement and this statement are logically equivalent. So after you have a truth table, you just look line by line and make sure that each row is exactly the same values, has exactly the same values. And so you see the statement here. They always have the same truth values, so they are logically equivalent. All right, it says rewrite the following statement in if-then form. Either you go to work on time or you are fired. Okay, so think about how you would write that in if-then form. And we can use this. All right, so we have either you go to work on time. So if you go to work on time, that is not P. You are fired is your cue. So we have our or. So it's basically set up in the first way, and we're going to rewrite it like this. So basically, we're rewriting an or statement as a conditional statement in if-then form. So not P is you go to work on time, and Q is you are fired. Okay. So we could also say that a P is you do not get to work on time. That could be helpful. So the equivalent if-then version is if you do not get to work on time, then you are fired. So let's go back and just look at that one more time. So we're writing this or statement as if-then, okay? Either you get to work on time or you are fired. So we negate this first part. So if you don't get to work on time, then you are fired. So you'll have a chance to practice that. So I encourage you to stop and really think about each of these and how they logically make sense. All right, we talked about negations. Negating a statement is simply changing its truth value. So by definition, P implies Q is false if and only if its hypothesis P is true and its conclusion Q is false. So I mentioned that already. So the negation of if P then Q is logically equivalent to P and not Q. And so we can state that with symbols like this. So in the parentheses, we have our if then. So the negation is, of course, represented with this little tilde. These three lines simply mean logically equivalent. And then here's our statement, P and not Q. So using that, try to write negations for each of the following statements. So I encourage you to pause the video and see if you can use this little formula to rewrite, to write the negations of these conditional statements. All right, if my car is in the repair shop, then I cannot get to class. Okay, so there's the if part, there's the then part. And so the negation would be my car is in the repair shop and I can get to class. Okay, so again, think how that applies here. So we keep the P part, we use and we negate the Q part. All right, so if Sarah lives in Athens, then she lives in Greece. So the negation would be, all right, Sarah does live in Athens and she does not live in Greece. Sarah lives in Athens and she does not live in Greece. She might live in Athens, Georgia, Athens, Ohio, Athens, Wisconsin, and of course, we have in Athens, Texas as well. All right, conditional statements have some various forms that you should be aware of, and one of the most important ones is the contrapositive because it is logically equivalent to its original statement. So if you have a conditional statement of the form if P then Q, the contrapositive is if not Q, then not P. Notice the hypothesis and the conclusion are negated and also switched. And so we could use the if then, but we could also use arrows. So if P then Q can be written as P implies Q is logically equivalent to not Q implies not P. So again, to emphasize, a conditional statement is always logically equivalent to its contrapositive. Write each of the following statements in its equivalent contrapositive form. So remember, when you're writing the contrapositive, you're simply going to switch your hypothesis and conclusion and negate them. And I think if you think about it, you'll see how they are, in fact, logically equivalent. It says, if Howard can swim across the lake, then Howard can swim to the island. We're going to switch those two statements. We're going to switch the hypothesis and conclusion and negate both of them. So again, if you want to pause this video and see if you could write the contrapositive of this statement, that would be a really good activity. Let's see how you did. If Howard cannot swim to the island, then Howard cannot swim across the lake. Again, the contrapositive. Switch the if and then portions of the sentence, the hypothesis and conclusion, and negate them both. All right, let's look at this second example. If today is Easter, then tomorrow is Monday. So we're going to start with if tomorrow is not Monday, then today is not Easter. There we go. So that's the contrapositive. There are two other versions of a conditional statement that you should also be aware of: the converse and the inverse. Now, it's important to note that while the contrapositive is always logically equivalent to the original statement, the converse and inverse are not necessarily so. The converse is simply switching the P and the Q. So if your original statement says if P, then Q, the converse says if Q, then P. And the two statements really are not the same at all, even though many times in the English language we do use those interchangeably. Logically, they are not the same. The inverse is the form of the statement where you do not switch P and Q, but you do negate each. Okay? Symbolically, we would say the converse of P implies Q is Q implies P. Again, nothing is negated, but the two statements are switched. In the inverse, we say the inverse of P implies Q is not P implies not Q. So this time, the two statements are not switched, but they are both negated. Notice that if you combine the contrapositive and inverse, you have the contrapositive. So if you switch them and negate them, that's the contrapositive. But if you just do one at a time, you have one of these versions. Let's practice. Write the converse and inverse of each of the following statements. So pause this video and try to write the converse and inverse of each of these. See how you did. So again, the converse, we switch the conclusion and the hypothesis. In the inverse, we do not switch them, we simply negate them. The negation of Howard can swim across the lake is Howard cannot swim across the lake. And the negation of Howard can swim to the island is Howard cannot swim to the island. All right, and then the second example, switching tomorrow is Monday and today is Easter. And in the inverse, not switching them, but just negating them. Now, it's important to note that if your original statement is in the negative form, for example, if your original statement said today is not Easter, remember the negation of that would be today is Easter. All right, so just a little reiteration of what I've already stated. The converse and the inverse are not logically equivalent to the original statement. Now, the converse and inverse are logically equivalent to each other because the converse and inverse are contrapositives of each other. Let's talk a little bit about only if and the biconditional. So P and Q are statements, and let's say we read a statement P only if Q. That simply means if Q doesn't happen, then P will not happen. So if not Q, then not P. So this is pretty important. You might take a moment to make note of that and really think about it for a moment. Let it kind of sink in about why that is true. Now, the contrapositive of this conditional statement is simply if P, then Q, which is why these are logically equivalent. So again, I encourage you to kind of pause and think about that for just a second. And here we can try it with an example. It says, rewrite the following if-then form in two ways, one of which is the contrapositive of the other. So they're wanting you to use this method and this method. Okay, so P only if Q means if not Q, then not P. Jack will break the world's record for the mile run only if he runs the mile in under 4 minutes. So this is our P. John breaks the world record for the mile run. Our Q is he runs the mile in under 4 minutes. So remember, how do we change this? Okay. If not this part, then not this part. So again, if you would like to take a moment, pause the video, and see if you can rewrite this. All right, let's take a look. So version 1, if John does not run the mile in under 4 minutes, then he will not break the world's record. Another way of saying that would be the contrapositive, and that's what version 2 is. Remember, in the contrapositive, you switch P and Q and negate them. Okay, so you take the second part, he will not break the world's record. You negate it and you put it first. If John breaks the world's record, then now take this hypothesis of this one. John does not run the mile in under 4 minutes. Negate it and put it here. He will have run the mile in under 4 minutes. Again, sometimes you just have to pause and really let that sink in, read through it, and think about it logically. Given statement variables P and Q, the biconditional of P and Q, P if and only if Q, is denoted by a double arrow. Okay, if and only if, which is also shorthand IFF. It means that the statement and its converse are both true. If P, then Q, and also if Q, then P. So we call this a biconditional of P and Q. When the statement is true, basically forward and backwards. Okay? It's true if both P and Q have the same truth values, and false if P and Q have the opposite truth values. So again, make note of this abbreviation, IFF, if and only if. It's a biconditional, meaning not only does P imply Q, but Q also implies P. Hence, we write it shorthand with a double arrow, showing that the statement is true forward and backwards. It's called a biconditional. Okay, so notice that in this truth table, this first two columns show all the possible truth value combinations of P and Q. It is true only when P and Q have the same value, like here and here. When P and Q have different values, then it is false. Rewrite the following statement as a conjunction of two if-then statements. So it says, this computer program is correct if and only if it produces correct answers for all possible sets of input data. So we're going to take our hypothesis, this computer program is correct, our conclusion, it produces correct answers for all possible sets of input data, and switch them, and they're both statements will be true. So the first rendition, if this program is correct, then it produces the correct answers for all possible sets of input data. Now the converse, switch the statements. If this program produces the correct answers for all possible sets of input data, then it is correct. So sometimes we have to change the wording just a little bit, just so that it goes along with the English language. For example, we wouldn't want to start the sentence, it produces the correct answers, because we're wondering, what is it? So instead, we say, if this program produces the correct answers. Okay, and I think this is one of the last topics for this section, necessary and sufficient conditions. I know this is a lot to take in. It's a lot of logic going on in this section. But again, sometimes if you really just pause and think about the English language, it does make sense in the English language as well as in our logic. Now, if you are an English language learner, that could definitely cause a little bit more confusion here, because it may not seem as obvious. But if you do have questions about it, of course, please reach out. Be more than happy to explain it further to assist you. All right, so think about R and S as statements. And it says R is a sufficient condition for S. Sufficient, okay, meaning when you think about the word sufficient, means it's kind of like it'll do, you know? And so if R is a sufficient condition for S means if R happens, then okay, S will happen. Now, it doesn't mean that that's the only way S will happen. It just means that it is a way. Now, necessary, think about this. R is a necessary condition for S, which kind of, it sounds like, okay, if R doesn't happen, then S won't happen, because it is absolutely necessary. So if not R, then not S. So again, this is something else I would pause and jot down in my notes: sufficient condition and necessary condition. And of course, we always want to try an example. It says, rewrite the following statement in the form if A, then B. Pia's birth on U.S. soil is a sufficient condition for her to be a U.S. citizen. Notice that's not the only way to become a U.S. citizen. You don't have to be born on U.S. soil, but if you are, that is certainly sufficient. It's a way to become a U.S. citizen. Okay, so we can simply say, if Pia was born on U.S. soil, then she is a U.S. citizen. All right, use the contrapositive to rewrite the following statement in two ways. George's attaining age 35 is a necessary condition for his being president of the United States. So, in the previous example, Pia being born on the U.S. soil will help her become a citizen, but it's not the only way. Here, George is attaining attaining an age of 35 is absolutely necessary. If that doesn't happen, he cannot be the President of the United States. So if George has not attained the age of 35, then he cannot be President of the United States. And we can say that with the contrapositive by switching the if and then. If he can be President of the United States, then he has attained the age of 35. All right, that is a lot of information. I wish you well. Please, again, reach out if you have any concerns about any of the topics that we have discussed here. Good luck, everyone.